I think everybody's at the department break-in ceremony, but that's fine. Oh, forgot to turn the thing on. So did everybody have a good day today? Good. Had a really nice chat with your advisor, Mr. Beck. We had a interesting discussion about the future of numerical simulation, and you know, it's funny that we both agree it's impossible, but he's going to try to do it anyway. So that's good. Have you slept on it, so now you want to argue it can be done? Good. He also told me that you can't kill Darcy. That we have to say that everything's going to be okay. And ironically, everything we see in here is still Darcy-like. So, you know. And I talked with Alex a little bit today about his research, and he's doing some relatively complicated modeling, and it still looks like Darcian regimes as well for that. So, but I wonder if it's all a coincidence. Who knows? Okay, so tonight, what we're going to do is go through a series of slides. We're going to jump right into the sort of precursor to petrophysics, but this is porosity and permeability relationships. Alex is going to be your man on the math review. I do have an enormous amount of travel coming up. Next week I'm out for 2 days, but I'll actually do 3 lectures. I'll do Monday, Tuesday, and Friday. And then the following week I'm out all week, and then the following week I'm probably going to be available more than not. So we'll see how that goes. And by that time we'll be more or less caught up with where I want to be. And Alex, you can take and do math lectures while I'm gone. And you don't have to use Friday. You could use the lecture nights. Just I'll go over it with you, but you have to correlate with Mary Lou on when you change the date. We can't just, it has to be like a day in advance. So, okay, my apologies, everyone. I thought I had gotten over the flu, and it looks like it came back. So when you're old, things like that happen. And I used to attack my illnesses with every drug known to man because my wife's a doctor, but then she cut me off, and I can't, I got to do over-the-counter stuff, and but you guys are tough. You don't need drugs, so I'll just tough it out without anything serious. So tonight we'll talk about clastics and carbonates, and be familiar with how porosity and permeability are related. We'll talk a little bit about what the concepts of primary and secondary porosity are, and then the things that affect porosity. And if you don't know what porosity is, math ladies, it's going to be the space between the grains. Okay, so there's a lot of space between the grains. Well, sometimes there's a lot, sometimes there's not a lot, but there is space between the grains, and that's really where the money is, because that's where the oil and gas are stored. And then we'll talk about correlative relations for porosity and permeability, and these are the old ones. These are the Carbon-Cassini equation, Berg relation, etc. And then we'll talk about the friction factor Reynolds number concept, and chemies. Who was chemie? Your first degree was chemie, right? You're not going to say them. Yeah, chemical. Sorry. And you too. Yeah. So you're going to like this because we're going to take it back to chemical engineering land. And we'll talk a little bit about why they did the kind of work they did, 80 years ago on trying to make a Reynolds number friction factor relationship. So what I'm getting at is, rather than use some empirical gradient rule, they tried to make a correlation of Reynolds number and friction factor. But it all depends on how you define the Reynolds number and friction factor. And again, ladies, Reynolds number and friction factor are dimensionless numbers. They represent clusters of information. And so what we were trying to do in mechanical and chemical engineering is relate basically pressure drop and velocity, but they make it dimensionless so it all fits on one graph. If I go too fast on that, please correct me, or elbow the Alex near you and he'll tell me what to do. So we have the following types of porosity. We have interparticle porosity, intraparticle. Interparticle is like the space between the grains. Intraparticle is where there's somehow porosity inside of the material. They show sort of carbonation materials here. There's also intercrystalline porosity, which would be like a dolomite. There's moldic porosity where there were shells of some sort, and during some period of time, those shells were leached out by water, some sort of acidic water perhaps. Then there's fenestral porosity, which is where you had organic matter that decayed and was eventually removed, and it left a pore space. You have shelter porosity, which can be shells turned upside down, things like that. And then you have growth framework porosity. Probably most of you are not familiar, but there's a big reef in Texas. It's called the Scurry County Reef Complex, and it's had a number of owners and operators, but I remember seeing a core from this thing, you know, the standard 4-inch core, and it looks like a gigantic piece of Swiss cheese. You can stick your fingers inside of it. And you can imagine if you've got that much porosity from a reef, that would be a growth framework type porosity, then you'll have a tremendous amount of fluid flow potential. In Saudi Arabia, there's something called a super K zone, and they don't really know for sure what it is, but it's mappable everywhere. They think it's about this tall, and basically it's a washout zone, so you could stick your hand in it. So essentially infinite permeability. I've been looking at something recently that was fractured, for all intents and purposes. There are a few reservoirs in the world that are made out of fractured granite or fractured basalt. Just shake your hands behind the door and it'll open. Yeah, there it goes. You don't have to open it for them because it has a heat sensor. And they were logging these things, and they would find a gap of like a foot missing. So, you know, maybe the blocks moved or that sort of thing. There's also cases like there's a field in New Zealand that's made out of boulders, gigantic rocks that have been overlain. And whenever you drill through it, the bit actually falls through the pore space if you're lucky. There's also in the Yates field in Texas, which is also a carbonate field, they would know they got to it because the bit would actually drop about 10 feet. So, you know, what I'm trying to explain is usually it's rock. You know, there's no gigantic pore space in it, but every now and then you come across something that does have gigantic pore space. You can also have fractures and channels. These are all things that are done after deposition. You can have vugs. Vugs are little holes in rocks, and then you can have caverns, which are caves, essentially. And then you can have things which are fabric selective or not. And we left the cores upstairs, but you can see that some of the cases I had that I showed the other day have boring and burrowing features. And do we have a geologist in the room? No. But who's Betty background? Okay, so remember when you took your geology class, there's organic matter, and what the bugs do is they get in there and they want to eat that organic matter, so they crawl around and they leave all this. And whenever it's completely distorted, they call it bioturbation. It just completely distorts it. There's a field underneath us here called the Curtin. Well, Curtin's off to the east, but it's the Bryan Woodbine, and the Curtin field is an extension of that. And we had some core from that. I think I may have a piece, and it's just completely burrowed and torn up and everything else, which does create porosity and permeability. And then you can also have shrinkage features in rocks. We were looking at a core the other day that somebody sent us, and it was in a faculty meeting, and you open the package of the box, and immediately you see all these shrinkage features. And obviously what those are is the core dried out, and it's essentially ruined, really, for further study. So you don't want to let the core dry out. That's why you'll see on the job site, they'll wrap it in foil and then dip it in wax so it won't dry out. They also keep it under pressure if that's an issue. But if you let anything with shale in it dry out, it's done. So next is discussion, and these are from Core Lab, about really microporosity. And microporosity includes clays. There's multiple types of clays, and some of them form filaments, and some of them form little curls or hairs, and then others actually form particles. And 35 years ago, this was probably the hottest topic in low permeability reservoir development, was these tight sands with these clays inside of them. And ironically, you know, shales don't have this, but shales are made up of clay materials. And it's kind of interesting. I mean, it's actually, the pore space is much smaller in a shale, but when we started developing shales with horizontal multifracture wells, some people said, well, we should go back into tight gas sands and tight gas oil systems and use multifracture horizontal wells, and it did very, very well. There can be maybe 3% porosity captured in that microporosity. It does not like water. Obviously, when you get water on it, it's going to trap that material. There was also a concept put forth by a geological consulting firm, which it sounds really sexy. It's called a permeability jail, which means that the permeability and the saturation of water conspire to not allow fluids to move. I think it was a really good way of selling their consulting services. But every now and then, if you type permeability jail in Google, you'll see a bunch of papers on it. But what they're basically saying is that you end up water blocking the gas from moving. They don't really talk about oil that much. Okay. Next is a discussion conceptually. I always like this slide because the reality from Keelan, this is a sort of a cartoon of a piece of rock, and then you have these holes drilled in a block. And you know, when I was your age, I thought that the holes drilled in the block were just fine. You know, it's sort of the Chem-E analog, right? Unfortunately, we have something called a tortuous path. You guys remember tortuous path? And so I can't walk directly to the door. I have to walk around to get to the door. That would be a tortuous path. And so there's a tortuous path in A, but the net result is that the velocity across this system is proportional to the pressure gradient or the pressure drop. And again, this is a cartoon just to explain conceptually how people see this. So we'll talk a lot about these kinds of models. The Klinkenberg effect, you have Dr. Akutlu for your advisor, and Dr. Akutlu loves the Klinkenberg effect, right? He loves to hate it, I guess. So the Klinkenberg effect is an effect at low pressures where gas molecules sort of bounce around, or they don't, they slip along the wall. And if you get small enough, you can imagine ping pong balls, let's say, and you're trying to put ping pong balls through a cardboard tube. If you have a large tube, then the balls, which represent molecules, sort of stay together. But if you have a small tube, it'll bounce around inside of there. And that's kind of the idea with the Klinkenberg effect. So it is a low pressure effect. The Klinkenberg effect is a small circle inside of a very large circle. And what's the large circle called? I guess you'd call it rarefied flow or diffuse flow. But it is a low pressure effect. The other effects that we would talk about are high pressure effects, but the Klinkenberg effect is a low pressure effect. So what's happening is whenever you have gas flow, the molecules slip along the walls. And when you have a liquid, they form a parabolic velocity distribution, which is what we typically think of with Puiseuille's law, which is flow in pipes. Now, you don't have to know anything about flow in porous media to recognize that whenever you have slippage, you're violating your rule. Okay? Your rule is that velocity and pressure gradient are proportional. But when you have slip, what's going to happen is that proportionality constant, if in fact it were valid that the constant of proportionality changed, that proportionality constant would represent a higher effective radius, which it's not. And so if you look at how the Chem-E's handled this in a steady state fashion, they created sort of a slip factor. But the slip factor doesn't really work. It does not model the Klinkenberg effect. I'm not talking about the theoretical stuff we do with rarefied flow. I'm talking about just adding a simple slip factor to Puiseuille's law or to Darcy's law. That doesn't work. It's actually a completely different flow regime. The way you compensate for this is you take measurements with gas at different pressures, increasing pressures. The higher the pressure, the more it behaves like a liquid, right? And so what happens is we cannot go to infinite pressure. And this is, 1940. So he recognizes that he needs to take measurements at 150 and 10 psi, let's say, 10 being the low and 10 being where you're going to have the slip. How would you correlate the results of that? Well, you cannot go to infinite pressure, but you can go to zero reciprocal pressure. So what he did was he said, okay, I'm going to plot the calculated results from the case where we have gas flow, and I'm going to take the reciprocal of the mean pressure, the pressure measured at each end, add them together, divide by 2, and then I'm going to plot that, and guess what happened? Well, you can imagine you get a nice plot, and it tells you what the equivalent liquid permeability is. Now, this is a more recent plot by Nelson, and the vertical scale has no meaning. Okay, everybody, vertical scale has no meaning. It's just a label. Just think about it as not really a graph, but the bottom scale tells you diameter or radii or whatever you want, but the upper scale is just sort of a label. Now, when you come over to this, the first thing you notice, and I put this on here so everybody would see it, is each line is 10 times smaller, obviously. And then they start talking about, okay, with an optical microscope, I can see this scale. With a scanning electron microscope, I can see this scale. With mercury injection, and what he's really saying here is with mercury injection, you know, it's meaningful at that scale. Now he can use some other, it says small angle neutron scattering. I have no idea what that is. Down here, what is computational chemistry? My chemical engineering friends. This is your advisor's new hobby. Okay? What is computational chemistry? It's where you consider the movement or the size of individual molecules and how they behave. So you can't measure it, but you can calculate it. Okay? And that's what we're talking about here. So these are extremely small spaces. Gabe, did you get some pizza? You're Gabe, right? No. Gabe? Cam, sorry. Did you get some pizza? Not yet. You're going to wait till it's cold. I know you're used to eating it off the floor the next morning in your apartment, but, you know, we're not going to go that route. Okay, so when I was your age, we only talked about this. I'm not joking. This is a scale. You know, we have the device downstairs that we use for the sonic sifter. Who's petty again? Did you guys remember the sonic sifter in your core lab? The thing that you put the sample in and it shakes it for 30 minutes or whatever it is, and then you go check and see, well, these are the sieve sizes that you're using. So the dust on that thing is probably the low end here. Okay, the stuff that you were collecting as dust is probably down here somewhere, maybe a little bit smaller. And we just ignored that. We said that wasn't even relevant. So over here, my whole career early on was using this. Now, you know, we're down here at this scale. So we're 1,000 times smaller than we were looking at 35, 40 years ago in terms of normal core analysis. All right? And you start looking at these things and you're saying, okay, so these are Jurassic shales, Devonian shales, source rocks, which are shales, Pleistocene shales, Pennsylvania shales, lower Cretaceous Travis Peak, which is low and very low permeability clastics or sandstones, Mesa Verde, which is in the Piazza Basin, and then you look down here, here's asphaltenes, which is bad stuff, here's ring structures, which is benzene et al., and here's paraffin hydrocarbons. In the oil and gas industry, what are we interested in? We're interested in paraffins. Okay, so roughly speaking, the size of paraffin molecules up to a certain size is about, okay, well, here's methane down here, here's nitrogen, here's helium, I guess hydrogen would be down here, here's mercury, here's water, and here's paraffins, and here's where our shales are. So we're in this category over here on size, and we're in this category in here in space, okay? So what's going to happen when the size of the room and the size of the molecules start to approach each other? It's a philosophical discussion. You're not going to be tested on this. I just need you to think about it. Before, and if you want, you can go work in the Middle East. You're over here. Actually, you're kind of over here, but that's a story for another time. Okay? How many oil and gas wells have been drilled in the United States? Rough guess. Over 1 million, right? Probably now well over 1 million. How many oil and gas wells were there in Iran 20 years ago? About 1,500. Saudi Arabia, about 2,000. Now they've gone on a drilling spree because they did some new developments. Kuwait is less than 1,000, maybe 1,500 now. So they're just blessed with a lot of porosity and a lot of permeability. We talked about the gas field in Qatar and Iran. Do you know how big those wells are? The tubing is 11 inches in diameter. Okay. And I remember I was in Iran, and these guys were telling me they couldn't flow any more gas up these things. And was there some way of painting the inside of the tubing with Teflon or something so it would flow faster? And I said, I guess you guys missed that day in, mechanical engineering class when you talked about friction and everything else. 11-inch tubing. Yeah. Some of these wells produced as much as 300 million a day. Now they don't produce that much continuously. They're a lot lower than that, but it's a lot of gas. Again, that's a dolomite. The South Pars North field, and there is a lot of. It's not. I don't think it's extremely permeable, but there's a lot of production potential. It's a thick zone. So how do you guys feel about this? I mean, you're looking at, we're burning class time, but you're looking at a methane molecule, and you're looking at a room that it's going to fit in that's roughly 20, 25 times bigger than that. Now, if somebody asks you what the minimum size for a fluid to behave normally as a bulk fluid, what would your answer be? Because obviously, if it's confined in a really small space, it's not going to behave the same. If the size of the room and the size of the molecule is almost the same size, thermodynamically, it cannot behave the same way. So there's this argument out there of what's the magic pore size, where you can use bulk fluid properties. Bulk fluid properties would be like this. This is my Coca-Cola and Red Bull mix, and you can see it. It's kind of dead, kind of flat, but the phase behavior of this would be predicted by sort of conventional thermodynamics. But if we went down and we put this fluid in an extremely small pore space, it would behave differently. So what's the magic diameter? Mr. Bay? Okay, I'll buy that. Depends on the fluid. Okay, depends on the pressure and temperature. Okay, but give me a ballpark. 1 nanometer is too small. Okay, so 20 nanometers will be over here, right? Well, roughly speaking, something like that. Okay, so you pick 20 nanometers as your cutoff. Anything below that, and you're going to have to do some sort of computational molecular dynamics model on the phase behavior. Okay, we can't really do that, so we cheat, but that's not for this class. Okay, so he says 20 nanometers. Anybody else got a vote? No? Can? No hobbling English? Okay, so they ran a bunch of model simulations at Colorado School of Mines. Your buddy, Dr. Cosme. And he and his team said it's 25 nanometers. And some other people said it's 50. Some other people say it's 100. So roughly, this is sort of your neutral zone here of where you may or may not be able to use bulk hydrocarbon fluid behavior. I know I spent way too much time on this, but this is important. Because at some point in your career, you're going to be faced with this question. So Alex, number 2, if you have to do a lot of work to figure out the computational behavior of the phase behavior, or you can just use a correlation, which one are you going to do? Right. And if you're wrong, what happens? You're going to hire Mr. Bake there to fix it? What is the outcome of being wrong, Mr. Bake? Right now, you're focused on volumetric issues. God, I did a Trump, sorry. But right now, you're focused on volumetric issues, not transport issues, not flow. But how much error will you introduce if you don't use the right thermodynamics? 30%. Too high or too low? Okay. So if you use bulk properties, you estimate 30% too high. If you use correct chemistry, correct phase behavior, correct thermodynamics, it's 30% less. Okay. Does that sound reasonable, everybody? Alex, are you willing to do 10,000 times more work for 30%? No. Yeah, pretty much nobody is. That's the problem. Now, we're talking in generalities, everyone, especially people out there in distance learning land. We don't know what the exact answer is. But if our calculated volume of fluid is wrong by 30%, where does that really hit us? Where? Nobody? See, this is a trick question. Sorry? Okay, there's an interesting point. Do we know that it affects us by 30% in our predictions? We don't know that yet. Rate predictions. Okay? We know that our calculation of in-place volume is wrong. But our calculation of estimated ultimate recovery is based on the area under the curve of rate predictions. So this is a circular argument. Which one is more important? And how many wells are being drilled right now in Permian Basin? Right this moment? Probably a couple of hundred. Do you think they're doing reservoir engineering on these? No. And what about when the Eagle Ford was being developed? And the Eagle Ford is much more compositionally sensitive. Okay. People were trying to think about this. And a lot of the work that you see in the storage aspects was in the Denver-Julesburg Basin or the Niobrara-Codell, or it was in the Eagle Ford. There's also a really wet spot in the Utica formation. So this is going to keep you busy for a long time. But if you have a group of engineers that you're serving as a technology person, what do you tell them? You tell them, you're wrong, but I can't fix this right now. Okay. By the way, do people really care about what the prediction is? I'm just curious. What do they really care about? Production, converted to dollars, converted to rate of return, converted to profit to investment ratio. I swear, every time I talk to young engineers and they start talking in terms of profit to investment ratio, I think in barrels, okay? I'm old. I'm tired. I think in barrels. Because you can tweak your knobs on profit to investment ratio, on rate of return. but you can't tweak your knobs on barrels. Okay. So the old guy, he's going to work on barrels. All right, we also have what's called, and I've been saying this, continuum flow is bulk flow, and molecular flow is where you would have sort of diffuse regime. So you have almost Brownian motion down here, and then you have Darcy flow over here. You can have slip flow in this regime, and then you can have transition in this regime. And again, you have essentially Brownian motion here where it's so diffuse it does this. And I helped the student create this, but you can see what you're looking at is sort of this low density gas. The molecules are bouncing all over the place. But then when you get to a much smaller pore, the molecules are packed much tighter. So we don't really have Klinkenberg effect in this. We have Knudsen effect. Okay. How much harder is it to calculate flow with Knudsen? Have you worked on that? No. Okay. Anybody? Okay. It's like non-Darcy flow. You have to have a pressure-dependent component because you have to calculate the mean free path. It's a nonlinear problem. You have to calculate the mean. You have to update it. It's a very interesting physical phenomena as well. If you're really interested in it, I had a student work on this with Dr. Morides and I, and it turns out that you actually get a calculated permeability that is much higher than you would think. Much higher. So the behavior of a nanopore flow system can actually generate a flow, a permeability, an apparent permeability is much higher than you'd think. And this is actually taken from that. Here what we were trying to do is just show the definition of the characteristic length versus the reciprocal mean free path and describe the different regimes. So this would be the molecular flow, which is Brownian motion, this transition, the slip, which would be akin to Klinkenberg, and then continuum flow, which is Darcian flow. And what you're seeing is that the actual permeability is down here at 10 nanodarcies, which is down here, 10 nanodarcies down here. But the pressure dependency of this, it actually shows that the permeability is much higher than it really is. And here, you're at 1 microdarcy, and you can see that the permeability actually is pressure dependent there as well. And in this case, the student was using methane, ethane, and water. So you really have to be careful how you represent this is the whole point. Okay, now we'll go back to the more traditional look. Again, we talked about looking at laminar flow, where you have a parabolic distribution of velocity. And what this particular article is trying to explain is what happens in a pore throat. So this is a throat of a piece of rock. And so you have an entering elemental volume, and then that elemental volume compresses. It compresses some more. It relaxes. And then as it goes back into the pore channel or the pore connection, it expands again, or sorry, it contracts again. So the onion diagram, low velocity flow lines look like this, higher velocity looks like this, and then you end up with an intermediate regime where you still have some characterization of the velocity with a streamline, but you also have these random eddies forming. And then high velocity turbulent flow is just a complete randomization of the flow field. I should have had this diagram back a few pages. I apologize. This is, and unfortunately, I took this graph from Klinkenberg. This is the permeability that's calculated from gas, and this is a reciprocal mean pressure. And what it's showing is that the higher the pressure, which again it's reciprocal, it converges to the equivalent liquid permeability. For carbon dioxide, what's the molecular weight of carbon dioxide, Mr. Ravikumar? 44, very good. What's the molecular weight of air? 28.96. What's the molecular weight of hydrogen? Okay. So the lighter the gas, the more effect. So if you use helium as your flowing medium, you're going to have to correct for it. Why do I mention this, class? You use helium for porosity, so they just turn, the machine does the same thing for permeability. So you're going to have to use it corrected. If you do not ask for the vendor to run the correction, your permeabilities will be much too high. Okay. This is just one of those little things you learned in class. It could be 3 times too high for carbon dioxide. It could be 5 times too high for air. It could be 10 times too high for helium. So be very careful. You know, it's like comparing one kind of currency with another. You have to know that it's been converted to some basis. Now, ladies, this is not something that you would ever think about, but if you're dealing with a phenomena like this, you have to recognize that it's pressure dependent. That's the key. But this is a laboratory effect. You're never going to see this in the field. But the laboratory, that's the floor below us, you can actually run these experiments, and you'll get exactly the same kind of profiles here. Okay. Now we'll talk about a few things, and I'm going to take a breath. Everybody ready? What do you say in India when you need to connect with your energy? Nothing. I had a professor from Taiwan, and he'd always go, "You must connect with your chi." Okay, so I'm going to connect with my chi. We're changing our minds completely now. We're looking at a correlation of permeability and porosity. Okay. Now this row, they've probably never heard of this before. Even the back row probably never heard of this before. But logically, the porosity is the size of the room and the permeability is the size of the door, correct? Everybody's okay with that? So permeability represents a cross-sectional area. Porosity represents the volume, normalized to the bulk. But the porosity basically is the size of the room. Permeability is the size of the door. Should they be correlated? There are 3 options. Yes, no, or maybe. Sorry? Okay, very good. This says that they're related by what? I'm tempted to try the pen. Hopefully it won't screw up the thing, but it probably will. It's a miracle. Okay. So this is a logarithmic scale. Everybody agrees? So that means that the y-axis is equal to some constant A multiplied by exp of some constant B times x, right? Now, why would that be true? Why? Anybody? Front row? Do you guys know the GOK theorem? Do you have the GOK theorem in math? Yeah. It's God only knows. Okay? Okay. It's a little joke. All right. So who was the first person to propose log of permeability versus porosity? Archie was, to the best of our knowledge. Okay. Should the size of the room and the size of the door be proportional? And you've said that it could be, that it would depend on the rock type, maybe it would depend on the depositional process, something like that. But should it be? Okay, now you're getting somewhere. If it's well sorted, is it going to be logarithmic? This is a trick question because we haven't covered this yet. First, we're talking about what Archie saw. But later, when people started doing experiments with unconsolidated samples and really sorting the daylights out of it, what did they get? They got a power law relationship, not a logarithmic relationship, but a power law relationship. And why would that happen? Because when you sort, then the size of the room and the size of the door would probably be proportional. Now, in this building, are the size of the rooms and the size of the doors proportional? Of course not. All the doors are the same size. Okay? So this is not a good example, but maybe. Also, this is a cartoon. What does cartoon mean? You know, I had an experience one time with a friend of mine, now a very close friend of mine, and his company makes software. And I was telling him, because he wanted to put it in a book, that you had to turn it into cartoons, that you couldn't just take snapshots of the software. You needed to make like publication quality plots. And I kept saying cartoon, cartoon, cartoon. And he finally screamed at me and said, my software is not cartoons. And if you don't shut up, I'm going to punch you in the mouth. So why am I saying that this is a cartoon? Because somebody drew this line, right? So how many data points were there? Something like this. I didn't draw my data points very well. I know this doesn't look like Chinese, okay, but these are data points. Little circles if you want, okay? What's the distance? You know, we could be as high as 200 or as low as 20. So somebody drew that line in there. If you go to your bank and you're supposed to have $50 in it, but you actually have 20, you're going to be mad. But if it turns out you have 200, you're going to be happy. But that's bad. You should have a moral code. You should have some integrity and tell them they made a mistake. But I guarantee you, if you thought you had 50 and you had 20, you'd complain. The real question is, you know, why would you want an equation that represents permeability and porosity? And should they be related? Is this enough? Okay. The answer, of course, is no. But we have to do something. Okay, so as I mentioned, to the best of our knowledge, this is the first plot. This is Archie's permeability versus porosity plot. It's from 1950. Archie has an interesting history. Archie's one of our gods in the petroleum literature. During World War II, he worked for Shell down in Houston, and those little round plugs I gave you, you know, he would experiment on them. He would determine the porosity and the permeability, and then he would also do what? Do you remember? Anyone? He would run an electrical current through them to determine their resistivity. Okay? And the question became, what is resistivity proportional to? Is resistivity proportional to volume, or is it proportional to permeability? Volume. You're absolutely sure. Yeah. Okay. Could it also be proportional to permeability? What are our three options again? Yes, no, or maybe. Maybe. But for the sake of argument, is everybody okay with Archie and his little plot and then later on his electrocuting cores? You're okay with that? So we'll talk about this a lot, but he's going to run a resistivity experiment on the core at 100% saturation, and he's going to correlate that with volume, as you mentioned. But he's also going to run the experiment on cores at less than 100% saturation, and he's going to demonstrate that resistivity is proportional to the saturation. And that did what for us? Sorry? Okay. What year was the first resistivity log? 27. Okay. And then what year was Archie's first paper on resistivity analysis? 42. So there was 15 years there where they were running all these, Marcel and Conrad Schlumberger were running these logs. But, you know, all they could do was see that it went this way, and then they also ran the spontaneous potential log, and it went that way. But they didn't know how to calculate something. So if you read Archie's 1942 paper, and back then they would take the discussion. So Mr. Ravi Kumar would write a nasty letter and say, Mr. Archie, you're just wrong, and you're stupid, and you need to, you know, get new clothes or something. And they said really terrible things about Archie. So he never published in the petroleum engineering literature again. He only published in the geology literature, which is what this is. So, little tidbit there. Okay. So we look at this. This is Mr. Schlumberger's, or the Schlumberger brothers log. So 1927, they ran their first log, and then, as I mentioned, I said 1942. Sorry, it's 1941. Archie first came up with a way of calculating something from that. And he was calculating porosity, and he was calculating water saturation. Now, a lot of things happened pretty quickly in those years. Did you guys watch the television series on Einstein? No? It's historically accurate-ish, but what was amazing was all the Nobel Prize winners in science and the things they invented. There was a really rapid explosion, if you will, of new science. And you could see those things were incorporated here in logging, especially the radioactivity stuff. And then here's another batch of things that were done. Can you estimate permeability with well logs? Anybody? We have one head going no, one head going yes. Explain how yes. Okay. Do you remember which log it is? It's the NMR log. And in order to calculate permeability, you have to have a flux. Okay. Schlumberger has spent billions, and other companies too probably, trying to figure out a way to cause a flux in the reservoir. And in the case of the NMR, what is it? It's a magnetic flux. So they have two spin times, T1 and T2, and they record these. They're actually more correlated with porosity, right? But if you calculate it to a piece of rock, then in theory you can relate it to permeability. Is there anything else you can do to estimate permeability? No? Yes? Maybe? Alex, what do you think the biggest challenge of the next 100 years is going to be? Thank you. No. Yes again. Ladies, what's the number one challenge for the next 100 years? What's more important than energy? Water. Because water is life. Where are we going to get our energy 100 years from now? Same place we get it now, from the sun. How are we going to do it? What's the biggest problem with wind and solar? Sorry? Correct, but if we put nothing but solar panels in the Sahara Desert, then we'd have all the solar panel generated electricity we want. Of course, those countries might not be very happy with us, but we could do that. What does electricity do when you transmit it? It has resistive losses, correct? So if you had a 10,000 mile transmission line, how much would come out the other end? Nothing. Okay. So that's why we have to have power plants that are, relatively speaking, near consumers. That's why we up the voltage to astronomically high numbers to move it. Okay. Can you store electricity? Sorry? How do we store it now? Batteries? Yeah. Is there any other way to store it? Sorry? Right. There's been work done on using excess electricity to pump water up a hill into a lake. They do that in the UK. There's also been experiments of using excess electricity to compress air into caves and that sort of thing. There's also been the obvious answer to me is to convert it to hydrogen. But hydrogen is the most abundant element in the universe, right? But you never find it in isolation. This is the trick of the next 100 years. Because if you had a free supply of hydrogen, electric cars wouldn't be necessary, right? What would we have? We'd have fuel cell cars. You wouldn't be worried about power stations. You just stick another fuel cell in. Interesting. Kind of a detour, but an important one. I could go off on a rant and tell you that nature's way of storing sunlight is oil and gas. You want me to do that? No, probably not. These are Archie's plots. This is his electrotherapy experiment. We have formation factor here, formation factor here, and he split the graph. Porosity is here, and then permeability is here. Okay. What year was this? It says 1950, but it was probably in the mid-40s that he did this. How deep could you drill in the 1930s and 40s? 3? You probably could push 6 to 10 in some places, you know. But I like your numbers, okay? I really do. So we'll compromise and say 5, okay? What does it say? Relation of porosity and permeability, formation resistivity, Natchitoches sand. Do you guys know where the Natchitoches sand is? I had a summer job in the Caddo Pine Island field near Shreveport, Louisiana. The Natchitoches sand is at about 900 feet. It's a water sand. Where we were, it's an oil sand about 10 miles away. Okay. 900 feet. Do you think that sand is going to be consolidated? Not at 900 feet. Okay. So this is relatively unconsolidated. And what you notice is that his correlation of resistivity and porosity is pretty good. His correlation of resistivity and permeability is pretty good. Here it doesn't really matter, but it's not so good there. Now, you made a comment about there may be some special conditions where the permeability and resistivity are correlated. But is it really permeability and resistivity that are correlated? Class? Very good. Very good. Very good. So what we've done here is we've taken all of Archie's cases, formation factor versus porosity, formation factor versus permeability. And you see these 5 plots, and this is convincing. Okay. Cam, you a baseball fan? Alex? Don't really care. Mr. Bate? Anybody else? Nobody likes baseball? Okay, Cam, we got to come back to you. If you hit the ball 1 time out of 10, how much do you get paid? League minimum. If you hit it 2 times out of 10, how much do you get paid? If you hit it 3 times out of 10, how much do you get paid? If you hit it 4 times out of 10, how much do you get paid? There isn't that much money in the universe. Who's the last person to hit 400? That's my point. So Archie had 3 laws that he proposed. Law number 1 was that porosity and resistivity were related. Law number 2 was that saturation and resistivity are related. Law number 3 was that permeability and resistivity were related. This is important. If that had been correct, we'd all be out of a job. How do we estimate permeability in situ? We use pressure transient testing, which is the whole purpose of deriving the reservoir engineering solutions. We will later. But if we could estimate permeability using resistivity, we'd be out of business as us petroleum engineers. That's not really true, but life would be a lot easier. But here, the data says that it's related. So you have a power law relationship for porosity and formation factor. You have a power law relationship for permeability and formation factor. How many of you really wanted to be an engineer when you were a kid? Nobody. That's nice. What did you really want to be? Comedian. Didn't care. Wanted to be president? Okay. Anybody else? Nobody wants to say? Okay. I used to take things apart, and sometimes I'd even put them back together. A friend of mine had a car that wasn't running right. He bought it in the UK, and it was a Fiat. He took it back to New Zealand, paid to have it shipped. And it ran okay for a while, and then it just really didn't run very well. So he hired a friend of his to fix it. And we went over to his house to see how he was doing. And the entire car, every part, was in buckets. You know, like the whole thing. And I said, you're up a creek, pal. This ain't never going to work. And so they ended up having to buy this relatively expensive part. It had to do with the intake manifold. And the guy put the whole thing back together. And as God is my witness, he handed him a bucket, and he said, this is what's left over. Okay? You don't really need these. Okay? I don't know what that has to do with this, but so if you set the permeability and porosity model equal to each other, what do you end up with? If you set the formation resistivity factor relationship for porosity and the formation resistivity factor relationship for permeability equal to each other, what happens? What do you get? You get a power law relationship between porosity and permeability. And where do we see a power law relationship between porosity and permeability? For highly sorted, unconsolidated sands. So there's the magic. The message here is that when you think you've invented the wheel, you might want to check and make sure that maybe it's not the wheel. So then we go to other examples where we're looking at this work. These are some actual cases from the Shannon Field. Does anyone know where the Shannon Field is? Eric? It's in southern Wyoming. And these are examples of porosity and formation factor relationships. These are actual field data. And you'll notice that the coefficient varies between 1.63 and 1.92 on one of them, and up to 2.38 and 2.87. And you can see that the difference is that there's shale in this case. Shale. Shale is a conductor, right? There had to be a villain in this story. Is everybody listening? So all this work Archie did was on nice, clean samples, and everything worked out reasonably well. But unfortunately, there's shale everywhere. And when you start having clays or shale, what happens? Those create an alternate circuit. So how do you fix that? Sorry? Yeah, there's some of that. There were some relatively simple correction factors for resistivity and porosity. But what about resistivity and saturation? Because now your conductor is varying and your villain or your gremlin is still part of the circuit. That was really tough. So there were some early so-called Shaly sand equations. Do you guys remember any of this from your well logging days? How many Shaly sand equations are there? Probably dozens. But the first one was Waxman-Schmidt's equation. And we'll talk about that when we talk about electrical properties. And then we talk about, well, do we really have power law relationships? And unfortunately, this was a geologist paper, and they made a really nice plot, and they used a power law equation, which is a curve on a semi-log graph. But at any rate, they were trying to show that they thought there was a power law relationship here. And then there was a guy named Papé, and there's a joke that I can't tell in here, but essentially Papé solved the concept of permeability using fractals, which is an extremely complicated way of representing something. You guys remember fractals, the thing where the part of a leaf expands? And he used the same concept to derive the relationship between porosity and permeability. And when he finished, he goes, ta-da, I've done it. But I don't have an equation. So what's rule number 0, class? Cheat. So he cheated. And what he cheated by doing was he said, the first thing I'm going to do, and you guys have to help me count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So that's 1 log cycle over and 10 log cycles up. So there's his slope of 10. That's that guy. Okay? And then he did 1, 2. Right? Oh, sorry, no. No, other way around. Thank you. Hey, I'm allowed to make mistakes in the interest of, learning, sort of. So there's 2. Kind of iffy there. Where's 1? Does anybody see 1 on this plot? And I did do that correctly, right? Yeah, I did. So there's something like that. And then he's got, so this is the 2 component. And then where's the 1? So when you add these 2 together, I guess you kind of get that curvy thing there. And what I'm getting at is he made this up. Okay. Later on, when Alex is teaching the math part of this course, what are we going to talk about, Alex? We're going to talk about the Gaver algorithm. And Gaver came up with a really clever way. I mean, an unbelievably clever way of inverting Laplace transforms numerically. But he needed an extrapolation formula. And he wasn't too good at that. So he created the most simple extrapolation formula he could. And then this guy by the name of Stayfest comes along 6 months later and says, oh, I see how to fix that. And who gets the credit? They call it the Stayfest algorithm. But it's actually the Gaver-Stayfest algorithm. So Papé, he put an enormous amount of effort into representing permeability and porosity using fractals. And then he created this half-breed, half-baked equation to represent it. I'm just kind of pointing this out, okay? So let's go back to data. Beard and Whale, they did a bunch of experiments with unconsolidated sand. And they had different diameters. They had coarse, they had medium, they had fine, they had very fine. And they also had extremely well sorted down to poorly sorted. And what you found was that depending on how well sorted it was, you got a different porosity. If it was extremely well sorted, you got 40% porosity. Extremely well sorted, 40% porosity. Extremely well sorted, 40% porosity. You see the point? sorting has an effect on porosity. Okay. So then we take these values and we plot them, and we're using average permeability divided by diameter squared, and we plot them versus porosity. And this gives us this trend. And then also Morrow had done some data on this as well, so we plot Morrow's data on here. Berg, from another study, said that the slope should be 5. I think it was actually like 5.3 or something like that. And 5 wouldn't be a bad fit here. But actually, Beard and Whale, Morrow's data, it said it should have been 8. What did Papé say it should be? 10. The real question is here, so what? What does this really mean? These are all unconsolidated or high permeability, high porosity type samples. What does it mean? Well, it means that we could come up with an algorithm or a relationship to represent this system by a power law relationship. Okay, well, let's talk about a few other things. Now let's look at permeability versus water saturation. And what you're thinking is that the higher the water saturation, the lower the permeability, obviously because there's nothing to flow through it. But if you're down at a low water saturation, your permeability should be much higher. And again, these are cartoons because there was more data than was shown here. The same thing from Timur. Timur tried to create a series of equations that involve porosity, saturation, and permeability. And this was used in the 1960s, actually it was published in 68, to estimate permeability from well logs. Okay? So you can see there's quite a bit of distance, I guess you'd say, or scatter for these. But at any rate, that's what Timur is trying to do. Okay. So some sort of relationship with permeability and saturation, and also integrating porosity into that. As I mentioned a minute ago, we have a relationship that is the power law relationship, but if we add some sort of dampening constant to it here, then that might improve its performance. And of course, my student and I, we spent a lot of time trying to figure out how to create a universal permeability relationship. And the simple answer is we didn't come up with one. But what we were looking for was somehow to modify the concept of a geometric relationship so that it represented this. And I know you're going, well, that's a pretty good fit, Tom. It's all right. It's not great, but it's okay. And then we also did the same thing, and we modified Archie's equation. So we considered this to be a clean sand equation, and we considered Archie's equation to be a dirty sand equation. I know it's time to go, but let me ask you a really quick question. I'm going to jump back to here where we were looking at Archie's porosity and permeability relationships. So why would permeability be logarithmic and porosity be Cartesian? Does anyone want to venture a guess? So I'm going to plot frequency. Stupid thing. I knew that was going to happen. How did I do that? This is going to be a bad day. Okay. We'll stay away from there. Okay, so I'm going to plot frequency, porosity, and yeah, I know my handwriting is terrible. Frequency and permeability. What do you think they're going to look like? This one will be normal. And if we take the logarithm of permeability, this one will be normal. Okay? I think that's where this came from. But, I'm not a statistician, and I'm not a student. I'm an old man who thinks like this. But I suspect that that's why this relationship works the way it does. is because looking at it as a distribution, you have a normal distribution for porosity and you have a log normal distribution for permeability. An opinion. Your job is to go figure that out. Okay. All right, we're almost done. The light's still red. This is from Fancher, Lewis, and Barnes, 1933. It's Mr. Desai or Prakar? Sarkar. Sarkar. Okay. What were you doing in 1933? Sorry? You were in heaven? It was before you came down. Yeah. Okay. Yeah, I feel the same way. I think I was probably a dog or a dandelion in my previous life, but they did this in 1933, and I included the book in your reference section. I think I may have made you read this. These guys did an enormous amount of work measuring velocity or rate and pressure drop through these samples. 1933. This would not have been a fun job. Mr. Bryan, I don't think you would have liked it either. Cam, you think you would have wanted to spend time in a lab in 1933 in Penn State measuring these things? You went to Penn State, right? Sorry? Well, they had one, and they were running all these experiments on rocks and lead shot and steel and sand and everything else. The quick question is, are all these curves the same shape? Mr. Bake? Yes, no, or maybe? Miss Wang, Miss Zhang, you think? Are they the same shape? I like big points and I cannot lie. Okay? So does that match? Yep. Does that match? Yep. Does that match? Yep. Does that match? Yep. Do the linear parts of this match? Yep. Yep. Does anybody want to tell me what this red line's name is? What's the name of that red line? Sorry? No. I mean, I agree with you. It could be called that, but it has a special name. Whose equation is that red line? Okay, I'll make it easy on you. This line, and I'll change the color. What's your favorite color? What's the name of the blue line? That's Darcy's law. What's the name of the red line? That's Forkheimer's equation. Why don't they all lie on top of each other? It's Gabe, right? Why don't they lie on top of each other? Is it Liu in the back? You want to help him? No? This is like The Apprentice. You're fired. Okay. What's the name of the red curve? In China, you eat with chopsticks. What do we eat with here? A fork? Yeah? So whose equation is this? Fork's equation? Forkheimer's equation. Okay. 1933. Some pretty crude data. They plotted their own version of a Reynolds number friction factor plot And they showed uniquely that a power law relationship exists between velocity and pressure gradient, which is Darcy's law, the power being 1 or minus 1. Okay? Why didn't all these curves lie on top of each other? Louder? The data is right, but they used the diameter of the particle, correct? The diameter of the particle is not the right characteristic length. So let's talk to our two chemies. What's the right characteristic length? Dimensionless numbers have to have the right characteristic components, right? The units worked. They were able to eliminate the units. They ended up with a dimensionless number. All the units, ladies, all the units canceled. Okay? But they used the diameter of the particle. Okay, the square root of that maybe, because they need a length, right? This would be an equivalent length. But the area would be really permeability, so this is getting into a gray area. Is there a characteristic length? Do you remember the Forkheimer equation? There is a characteristic length in the Forkheimer equation. So if we jump forward 20 years and we go to Michigan from Penn State, the same data, Cornell and Katz figured out the right y and x-axis plotting functions. Okay. So this line that they've drawn is Darcy's law. And this line, or this curve, is Forkheimer's equation. So right now, we're in 1953, and we have an equation at our disposal that is a universal relationship between velocity and gradient. Okay. Now, if this were the Moody friction factor diagram, there would be more than one curve out here, right? But if we've defined this thing right, we may have captured everything. There was some mechanical engineering versions of this where they used other materials, in particular sintered metals. You guys know what sintered metals are. They're little balls of metal that are compressed into sheets. They use them for air filters, that sort of thing. Okay. There's all sorts of things that they use this kind of stuff for. So this has also been validated for that sort of stuff. Okay. Fuel filters, air filters, other kinds of things. Okay. This is where we're going to stop tonight because there's a big question mark. And what's a question mark? Why didn't we use Forkheimer's equation everywhere? Cam, you want to take a shot? What percentage of petroleum reservoir flow behavior is covered by, say, this? You want to speculate? No, thank you. Let's just say conventional systems, I guess. Greater than 0.01 millidarcy. Probably 99% of the flow in those cases is covered by that box. Okay, maybe it's 98, maybe it's 99.5, but essentially everything is covered by that. It's when we start getting into lower permeabilities where we start having that deviation, right? Yes?
Gases and high permeability also have that?
I hadn't really thought about it. I guess we'd have to look at how it plots on the chart, but good question. It would probably move the box to the right a little bit, or to the left, I guess. Sorry, to the left. Yeah. So this is a very interesting discussion. we just went through some historical aspects. And what we've come up with is that Darcy's Law is probably going to work for everything we want it to work for. Circa 1980, probably. Maybe 1970. Because really, the work on non-Darcy flow effects started in the 70s. But, so why didn't we use Forkheimer's equation everywhere? Forkheimer's equation says that pressure gradient is equal to velocity multiplied by a constant plus velocity squared multiplied by another constant, correct? That's what that term is. That is that when we combine that as the equation of motion with the equation, the continuity equation, what's going to happen? It is not going to be solvable. Okay. We have to do it numerically or use a perturbation type solution. Last question of tonight. What does this flat portion tell you? It tells you that no matter how much you increase the gradient, you cannot increase the velocity anymore. Exactly the same as we did with the friction factor plot for pipe. Okay. So at that point, friction effects take over everything. You guys have had enough. We'll see you on Monday night.